So as we move along, we'll finally finish up these axioms. Axiom 7 is the next one we'll talk about. This is called the Power Set Axiom. And this is a construction/existence axiom that tells us that for any given set, we can form what's called the set of all subsets of X, or the power set of X, as it's sometimes called. Not just sometimes called, but this is always what it's called. So that if X is a set, then there exists a set called curly P of X, called the power set of X, the elements of which are every subset of X. So for example, if A is the set A, B, C, the power set of X, or power set of A, is the set containing the empty set, because that's a subset of all sets. The set containing A, the set containing B, the set containing C, the set containing A and B, the set containing A and C, the set containing B and C, and then lastly the set containing A, B, and C, or A itself. And you can immediately note that the number of elements in A, which we call the cardinality of a finite set, we'll define this a little bit later on, is 3. And the number of elements in the power set of A, or the set of all subsets, is 8, or 2 to the cardinality of A. This is an intriguing thing that actually holds in general, not just for finite sets, but also for infinite sets. And this is a very important thing to think about. We'll define what an infinite set is a little bit later on, but it's really going to take the next couple lectures to really understand what is meant by this idea of an infinite set. But what you will see is that you can immediately see that for this 3-element set, the set of all power sets is 2 to the cardinality of the set right here. And when we get more into counting, right, we will be able to directly show this, which is very, 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 very neat. And we can write down a definitive proof of this. So I'll just give one more example, maybe a more practical example, and it's related to a previous example that we talked about. We talked about the sample space for a given deck of cards being the Cartesian product, the set of all ordered pairs, of the rank of the cards and the faces of the cards. Specifically, for a given, this set right here, the sample space, is going to be everything from the 2 of hearts all the way up to the ace of hearts, everything from the 2 of diamonds all the way up to and including the ace of diamonds, the 2 of clubs all the way up to and including the ace of clubs, and the 2 of spades all the way up to and including the ace of spades. Remember, we computed this as the Cartesian product of the set of 4 faces and 13 ranks to give us a total of 52 elements in our set. So the power set of this, and in probability theory this is called the sample space, this R cross F right here, but the power set of this R cross F is going to be the set of all subsets, set of A, such that A is a subset of R cross F. So this is the length 1 subsets, or the singletons, the length 2 subsets, the length 3 subsets, and so on and so forth. But for a particular card game, say a 5-card stud or a 5-card poker hand, what we're going to be interested in is the subset, or the subset of this power set, call it curly B right here, such that this is the set of all sets B, such that B is an element of this power set, and B has 5 elements. A little bit later on, when we get into counting, we will show how to actually count exactly mathematically the number of elements in this set. However, the total size of this set is extremely important when calculating probabilities in poker. And this is a very, very practical example of where the power set comes in as a very important thing in mathematics. I mentioned before that the relationship between the cardinality, right, of the relationship between the cardinality of the set A and the power set, this set, right, the cardinality of the number of elements in this set, the power set of R cross F, is going to be 2 to the 52, which is a huge number, very, very large number. But because of this relationship that we have for finite sets, we actually have a slightly different notation that you sometimes see for the power set. I want to note this right now. The power set of a set A is sometimes noted in some sources to the A, which is not a number. This is saying the 2 symbol and then raised to the A. And this is sometimes seen as a notation of the power set, but this is actually a different set. So that is set theoretically isomorphic, or in bijection with the power set of A. Now, I have not defined what in bijection with or set theoretically isomorphic mean yet, but rest assured in the next lecture I will do this. The idea here is that this means that the power set of A, the notation for this is this symbol right here, and you see the power set of A is set theoretically isomorphic to the set 2 to the A. So the set 2 to the A is the set of all functions from A to a binary set and we'll be able to show that these two things actually have the exact same number of elements, even for infinite sets, which essentially means, right, that the cardinality of these two sets are the same. We can form what's called a one-to-one correspondence between the two sets, or a bijective mapping between the two sets. And this is actually the basis of cardinality when we go through and actually define for a general set what the idea of cardinality is. We have to use this concept of functions that will be introduced at the end, or a little bit later on in this lecture. But so the last axiom for Zermelo-Franco set theory, which is ZF set theory, is Axiom 8. Remember, there are 9 axioms, but Axiom 1 through 8 essentially give us what's called ZF set theory, or set theory without the axiom of choice. This is the axiom of infinity. This is the axiom that an inductive set exists, which means that we can essentially do a union operation ad infimum, or repeatedly, to get what's called an inductive set. And what I mean by an inductive set is that an inductive set I is a set such that the empty set is an element of I, and that if X is an element of I, so it's an if-then statement, if X is an element of I, then X union the set containing X is also an element of I. The idea here is very special. The idea behind why we introduce the axiom of infinity. The main idea is that it allows us to now construct and talk about infinitely sized sets. And for a perfect example of this, I'm going to talk about the formal construction of the natural numbers. And you'll recall that kind of intuitively at the very beginning, we think of the set of natural numbers. We wrote this down as the following set. And I talked about, at the very beginning of this lecture series, what does this ... mean? And the question here that we want to think of is, how can we explicitly define this? And we can define this as follows. From axiom number 1, well, if we identify 0 with the empty set, then from axiom 4 we define 1 as, or we identify 1 with the set containing the empty set, which we know is a valid set. We can then identify 2 with the set containing the empty set and the set containing the empty set, which again is from axiom 4, is a valid set. We can then identify 3 as the set containing the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. And now what we have then is that the natural numbers, the set of all natural numbers, is a result of applying Axiom 8. Or the inductive, the Axiom of Infinity, which is that an inductive set exists. Because if a set of I exists with this property, that means that every and all possible combination like this is included in the set. And this is exactly how we define the natural numbers. And these are also called what are called the von Neumann ordinal numbers, which I have a little table over here. First four or five von Neumann ordinal numbers. So the idea here is that typically when we're doing mathematics, we think of n as just 0, 1, 2, all the way up to any positive number we want. But the idea here is that really this is what's called, it's set theoretically isomorphic to this construction right here, where the empty set is 0, the set containing the empty set is 1, the set containing the empty set and the set containing the empty set is 2, and so on and so forth, all the way up to infinity. So this is a very, very neat construction, and there are other ways of making a construction of natural numbers. However, this is probably one of the most important and one of the most standard. So what I want to do right now is make functions a little bit more specific and kind of give you a couple examples of functions before the next lecture, so that we have an idea of what types of properties we're going to be proving in the next lecture, because the next lecture will deal all with function properties. So I'm going to define what a function is right now. Say let A and B be non-empty sets. A function from A to B also called a mapping or a transformation. These are synonyms. Is an assignment of exactly one element of set B for each, or to each element of A. We write f of A, if the function is f, we'll say, and typically, F, G, H, W, these are all letters that are used for function. We'll call our function f. So we write f of A is equal to B if B is the unique element of B. Assigned by the function f to element A of A. The notation here that we use for functions is first very, very important. So I'm going to make a very, very important remark right now, that for a given function, if f maps A to B, this is the notation that we give, and then we typically include some words or an explicit definition after this of what the function actually does to elements of the domain of the function. But this set right here, this notation stands for f, the function maps set A into set B. This set is called the domain set. And this set, B, is called the codomain set. I want to be very specific here. This is different than the range of the function. In general, the range of the function is smaller than the codomain set. And if the domain set changes, or the codomain set changes, the actual definition of the function changes. So certain properties we'll see explicitly depend on the choice of the domain set and the codomain set. So keep that in mind when you're writing down a function, that it's always important to specify what exactly we're talking about for the domain set and the codomain set. You need to specify these when you're talking about a given function. But we can draw a little diagram here to maybe better understand this. If this set right here is set A, and this set right here is set B, this is the domain, and this is the codomain, then for a given element of A, x, the function f maps x into B, where this is f of x, and the explicit mapping is defined up when we define a function typically. But the idea here is that we can now say that in general a function maps a set A into some subset of the codomain. This subset of the codomain is called the range, and it's denoted by f of A. So the range here is this set right here, f of A. And I can write that down right here. It's a definition. The range set of f is denoted and defined by the following. Set. So if the domain is the set A, we say that the range of the function f is denoted by f of A. This is a set. It's the set of all y in the codomain B such that there exists an x in the domain such that f of x is equal to y. Right? And by definition, right, this is always going to be a subset of the codomain. An equivalent definition would be the set of all f of x such that x is an element of A. The idea here is that we're just saying that for any and all x, in f of A, we can find at least one element of x that maps to that element f of A, given the function f, or the function f maps to that. And if we take all of the elements in A and find their mapping, this is exactly what we have. Now I'm going to copy this image because I have a couple more definitions that are related to this picture. This is a very, very good diagram to use to define the following concepts. First things first, for a given element of A, we say that the image of an element x is the value that it's mapped to. F of x. So, for instance here, if y is an element in the range set f of A, this means that there exists an x in A such that f of x is equal to y. There could exist many x's such that f of x is equal to y, so be careful about that. The there exists statement is not a unique statement. This is just a general existence statement. Right, we have that each value x can only be mapped to one element y. So the idea is that each one of the x values, or the values in the domain, can only be mapped to one element in the range. But multiple values in the domain can map to the same value in this range. So be careful about that. This is actually going to be related to a fundamental property of functions that we'll get into next lecture called injectivity. But we say that the image of x in this example is y, the element y, or f of x. And there's a definition of what it means to say the image of an element. We say that the pre-image of y is x. And I'm just going to put y in here because this is what I'm using. So x is being mapped to y. And then what I also want to write down is the fact that these ideas, the image and the pre-image, both of them, extend to actually subsets of the set A and subsets of the set B. What I mean by this is the following. The image, or image set, and it's sometimes it's just called image, of a subset S of A is defined as follows. It's the set of all things that are mapped to. So this is, say, a subset S. This will be mapped to some subset in the range set, which we call f of S. So if S is a subset of A, then we see that f of S is the set of all y in the range, or even in the codomain B, you can say, such that there exists an X in the set S such that Y is equal to f of X. Right, so we don't have to just restrict the image to this whole set A. You can actually take the image of any subset of A that is inside A, and this is a very important idea when we go through and do this. Functions, in specifically definition of continuous functions, the correct topological definition relies on this idea of the image in the specifically what's called the pre-image. So the pre-image of a set is the next definition I'm going to make. The pre-image and really this is a set, pre-image set of some subset of, we'll say a subset W of B is defined as follows. And this notation will be familiar to you if you understand and recall definition of an inverse function. But we need to be very, very careful here. There's no mention of an inverse function. This is only a notation for the pre-image set, because very often we have that inverse functions don't actually exist. But we can always define the pre-image of a subset B. If B is some subset, or W is some subset of B, maybe like this, then the pre-image is the set of all values in A that map into this set W. So this is the set of all X in A such that f of X is an element of W. Oops, and I need to be very careful here. The pre-image of W. So with these basic definitions, we are good, and we can kind of go on and investigate some simple examples. And for the very beginning, what I'm going to do is I'm going to actually use the following relatively simple examples, and I'm going to do an example of something that is a function, an example of something that is not a function. So we'll say the mapping in both cases is going to go from A to set B, and we'll consider the following two examples. where the arrows here is denoting what how the function is behaving. This is an example of a function. Because each element of the domain set A has one and only one value in the range. However, this is not a function. Because not every element in the domain is mapped to one value in the range. The violation here is that C is being mapped to two separate values, therefore this is not a function. However, this is an example of a more general object called a relation. Which is another object that we're going to study very heavily in this class. And actually all functions are a special type of relation. All functions are a relation, but not all relations are functions. I'm going to make a note of that right here. A relation between two sets A and B is a subset of the Cartesian product. Between the two sets. And I want to note that every function is a relation. But not every relation is a function. In general, we have many more relations for a given two sets than you do functions. And we're going to start by studying functions first, because this is going to be how we really define the cardinality or counting between sets. However, relations are also extremely important in constructing new mathematical sets, so we're also going to study these in depth as well. So the takeaway here is that we can visualize kind of this specific function, in general any function, in terms of the set of ordered pairs. This is A comma E, B comma E, and C comma F, this specific example function right here. And same thing, we can visualize this relation, or we can write down this relation as the set of ordered pairs A comma E, B comma E, C comma E, and C comma F. And so the idea is that the reason that this is a valid relation is that this is a subset of the Cartesian product between these two sets A and B. This is also a subset of the Cartesian product between A and B, but this is a special subset because each of the domain elements of the function A only appear once in this this subset. And this actually leads to the definition of the graph of a function as well. those all ordered pairs of the domain and range elements. Or GR, the graph of the function f, is the set of all ordered pairs x comma f of x, where x is an element of A, the domain set. And so we're finally at a point where we can write down the final axiom in standard set theory that's used in most modern mathematical theories. And this is Axiom 9, the axiom of choice. This says that for every set S of non-empty disjoint sets, there exists a function called a choice function defined in S, such that for each set X in S, we have that f of X is an element of X. This basically says that we can, for any non-empty set of non-empty disjoint sets, we can choose elements from each one of these disjoint sets. Initially you might not see the purpose of having this axiom, but I can assure you this axiom is extremely important and used in modern mathematics for a reason. The main idea here is that if we have a collection or a set of non-empty disjoint sets, we can find a function that selects out an element from each one of these non-empty disjoint sets, such that the function on each set is an element of one of these original sets themselves. So this diagram very nicely kind of illustrates this point. And I want to note here that the axiom of choice is independent of the other 8 axioms of set theory. The first 8 axioms, if you only take these, this is called Zfc Set Theory. But with the axiom of choice, you have the 9 axioms. You have what's called Zfc Set Theory, which is what what most theorems and constructions in modern mathematics is based off of. And standard mathematics uses the axiom of choice, and hence so will we. There's a number of theorems that can only be proved by using the axiom of choice. So, and this is the reason that we're choosing to also use the axiom of choice. So examples of such theorems are that every vector space has a basis, which is both these terms are defined in a linear algebra course. This is an extremely important theorem. The theorem that there exists a complete system of representatives of an equivalence relation and an equivalence relation is a very special type of relation that is very important that we'll see in mathematics. But this theorem can only be proven using the axiom of choice. The well-ordering theorem in set theory is that the theorem that every set can be well-ordered. There's a whole list of other things that can be shown to be equivalent or proven using only the axiom of choice. Zorn's lemma is another example, but you can do some research and find a list of all the others. I'm going to put ... here because there are many other things that in modern mathematics that require this axiom of choice. But this will conclude the lecture. Thank you very much for tuning in, and I hope you had a fantastic day today.